have certain properties. Like, well, I'll give you one example. The concept of a prime number, right? That's an example of a mathematical object, a prime number. Assume you know what a prime number is. And you'll give it, these prime numbers, you give it a certain property. For example, there's an infinite number of them. Okay? That's your suspicion, that's your conjecture. The prime numbers go on forever. There's no last prime number. That becomes your conjecture. That's what you. So your theorem statement might be there are an infinite number of prime numbers. Okay, and then you try to prove that that's the case. And there was a famous proof about 2,000 years ago that there is no maximum prime number. That would be an example. Okay. So you make these statements about your objects, the properties that they have, and then you go about proving that that statement is true. So these statements usually you can call a theorem statement. And once you've given the proof of that statement, the statement and the proof together, I guess, you call a theorem. Or some people, well, it depends. Some people just call the statement itself the theorem once it's been proven, but they don't supply the proof. They just, the statement becomes a theorem. For example, famous theorem, Gödel's incompleteness theorem, and it's just a statement. It's not the actual proof. The actual proof takes a whole book, pages of it. But the theorem is just the statement itself. But because you're using the term theorem, that implies that statement has been proven. It's been proved. And if it hasn't, well, you can't call it a theorem. Theorem implies the existence of a proof. Okay? Right. Now, what is a proof? Well, it's a logical argument that's extremely persuasive. Well, it has to be actually totally persuasive, no exceptions. Right? Absolutely airtight, watertight. There can't be any question of doubt. It's total. It's absolutely convincing. Right? So, and what's a theorem? Well, it's a mathematical statement that has been proven in the past to be true. Okay? If it hasn't been proven yet, cannot call it a theorem. Right? I've mentioned some of these technical terms a bit already. The notion of a lemma. Okay? So a lemma is sort of a mini. I'll just say it again, a bit of revision. A lemma is a sort of mini theorem, and typically you'll use the word lemma with the implication that you're going to use it again, the result, later in a bigger proof. So a lemma is a sort of preparatory mini theorem. Okay? And a corollary is also a theorem, but it follows after the main theorem. And usually a corollary, the implication is, the connotations are that it follows fairly easily. You can deduce it fairly easily from the main theorem that preceded it. Right? So typically the time order, as you're reading through a textbook, I could probably find examples here fairly quickly. You'll have quite often maybe one of several lemmas, like preparatory mini proofs, and then you'll have the main theorem, or the proof of the main theorem, the theorem statement, and then the proof. And after that, you might have one or two corollaries, like mini proofs that follow relatively easily, from the main theorem. So let's see if I can find, looking towards the back here. So I'll get him to say, now this is the abstract algebra text. I just ran a page. Well, I found theorem, corollary, theorem definition. Maybe I might, if I can't find it quickly. Definition, corollary. Definition, theorem, corollary. Definition, theorem, corollary. Ah. Okay. Here's one. Lemma. Definition. Theorem. Corollary. Yeah, there's one. Okay. So that's fairly typical. Yeah, those three in that order. So lemmas first, usually, preparatory mini proofs, then the main theorem, and then corollaries. So if you like, if you make an analogy with cuisine, cooking, you can look on the lemmas as the hors d'oeuvres, the preparatory dishes to whet your appetite. You can look on the main theorem as the pièce de la résistance, the main meal, the bulk that fills you up. And you can look on the corollaries as sort of the dessert, the sweet things that come after. Right? Okay, so lemmas and corollaries. Now, how do you... it's a bit of a joke almost. How do you find proofs? Now, proving theorems is, well, yeah. Finding proofs is not always easy. And I put a winking emoticon here. That this is an understatement, believe me. It's almost a joke. Some proofs are so difficult that it requires real genius to do them, to perform them, to create them. Right? That's personally, when I look at what some very rare pure mathematical minds are capable of, like you get the occasional super genius, IQ over 200, and they just create what I call cathedrals of logic, mathematical logic, and they just seem to be able to churn it out, like pages every day. There's a famous group theory mathematician. His name's Thomson. Well, he was at Cambridge University. I don't know if he's still there. Even when he was a graduate student, he was churning out like 10 pages a day and giving it to his supervisor, who was just in awe, just jaw dropped at the incredible productivity of this student. Anyway, he went on to become the virtual god of group theory, the top group theorist in the world, and he could prove things that virtually no other person on the planet could do. So, finding proofs for theorem statements can be very difficult. Now, some of the exercises, as we get into this course, of course they'll be much easier, otherwise they wouldn't be in the course. But you'll come across theorem statements and you're asked to prove them, and you'll get stuck. You'll find, gee, this is hard. So proving stuff is an art. Right? There's no obvious recipe. There's no here's a proof statement. Put it into a machine and turn the handle and crank out the solution. Crank out the proof. It doesn't work that way, right? It's a creative process, and the more experience you get in proving theorems, the more you'll see that theorem proving is an art, an ART, an art. Okay. So you can't reduce it to a recipe. So what do you do? How do you go about finding proofs to theorems? Well, there's no recipe, but there are some guidelines. Like there's there are certain rules of thumb, if you like, heuristics as they're called, that help. And you pick these up from experience just by solving lots of problems, proving lots of things, and you get experience after a while. You get a sort of intuitive feel for what approaches are practical. Now, in the coming sessions, we will cover various proof techniques, various strategies that get used a lot in theorem proving. That we will use in the course, that the many theorems in the course use. So various proof strategies. Okay, but that's for that we won't do it here. Well, we'll just start actually, but that's for next session, next board. So rules of thumb. Like firstly, read the theorem statement very carefully. So it's clear what it is that you're asked to be proved, right? So read it carefully, and maybe you're not too familiar with the notation, the various symbols that are used, and what do they mean, and what the definitions are. So you need to get into the problem in that sense. So what's the notation? What are the definitions? Stuff like that. Now, in some cases, you can take the problem that you're talking about, so say you have to prove something, and you might be able to break it down into parts, divide and conquer, that kind of approach. So you take a problem, you break it into pieces, and then you solve each piece individually, like one after the other. Now, a particular type, a particular example of that kind of thing in finding proofs is something called, you'll see mathematical statements of this kind. A mathematical statement P, whatever it is true if and only if, and then some other mathematical statement Q is also true. So P is true if and only if Q is true. And often it gets shorthanded, written this way, P, if, if and only if. P is true if and only if Q, or P if Q. Right? Now, if you see that kind of thing, then you have to break it down into two parts at least. If you're asked to prove P if and only if Q, you have to prove two things. Well, I'm starting. Now I'm getting ahead of what's written here, but I'll just say it. You have to show that if P is true, then Q is true. You have to prove that. And you also have to prove it in the reverse direction. So you also have to prove that if Q is true, then P is true. So it's a two-part proof. Okay, so that would be an example. So the if and only if type theorem statement is a clear example of a multi-part proof. Well, in this case, a two-part proof. Right? You have to prove if P is true, then Q is true, and you have to prove if Q is true, then P is true, in the opposite direction. So it's a sort of two-directional, two-part proof. Okay? So, well, we're just touching now on a longish section, portion on proof techniques. So we'll do that next board.